for the application in the spintronics, because at the 0 field here you can have the 0, 1. So for example, so the bit 1 and here bit 0. So the whole 1 bit 1 and 0 is where to find in the 0 field here. Okay. And then, so we can see how is intrinsic explanation for the detailed explanation of the existence of the exchange bias field. You can see here. So we go to the near temperature here, and we cool down, and we form a spin ordering of the spin anti-ferromagnetism here. And you can see, according to this exchange bias hysteresis, you can see the magnetic field go from this direction to this direction, and you can see here go to this direction. And you need to have a stronger field to switch the magnetization from the left to the from the right to the left here, and go back. You can prefer again go to this direction here. So the magnetization here is prefer into this direction here, to the right direction. That's why you have the spin. The so-called exchange bias field. This is a microscopic description. So the relative orientation of the ferromagnetic spin and the anti-ferromagnetic spin at the interface give you energy minima along the one direction here, along the one unit direction. Okay. So this is an explanation. But till now, the anti-ferromagnetism can be only used in this so-called, we call this spin warp system, or called the exchange bias system. So, and in this way, so how to get the perpendicular anisotropy? Usually go back to the perpendicular anisotropy. So usually you put a film here, and then you have a dipole-dipole field. So the most of the film prefer to go to implant because of dipole-dipole interaction. So it's very difficult in terms of energy, dipole interaction energy, to support magnetization along the perpendicular direction. So and then that is many ways. There are many ways to get the perpendicular anisotropy. One way you find some so-called interface anisotropy. You have the interface aberration to provide the ferromagnetism and extra perpendicular anisotropy term. So because you have a symmetry breaking, and you can provide an extra orbital moment, a strong orbital moment to support the perpendicular anisotropy. There are many ways. This is not new. The usual way new. And there are several materials, and you can also try to find a unit anisotropy for some LOE. Basically, the crystal structure provide already a one direction preference of the crystal structure, and in turn also magnetization orientation. And there are many thin-film systems. So these are all. So what I'd like to say is our system put the ferromagnetic and anti-ferromagnetic together is beyond this distance. Here, so some system here is all at the beginning is you are perpendicular and go to the implant and so on in a different system. Okay, this the perpendicular anisotropy. And in this talk, I will show you the normal perpendicular anisotropy system here. So by using the exchange coupling between the ferromagnetic and anti-ferromagnetic. So I'm going to show you the experiment. And how to find the experiment, and how to actually the starting experiment. We use a lot of the singleton radiation. Singleton radiation. You can see the pin here. So one of the very powerful tool in singleton radiation is the spectral microscope. Spectral is you give the energy, the information, the energy, and here microscopic give you the topographic information here. So then spectroscopy give you the information of chemical, and it become the element specific here. And the microscope give you, of course, the information of the morphology here. And then you can see this is a standard so-called the MCD measurement here. So you can use a circular polarized light here, go to, and you have the spin. This is magnetic material here. So basically, so you can have observe your absorption here. So you have a ray line here, and you can see here there's a different intensity from this direction. So basically, if you have the same direction, the the parallel direction between the circuit polarization and the magnetization, you have a higher intensity in this case. And if you have a low intensity, but you have an anti-parallel orientation between both. So then you can, from this one, then you can use a circuit polarized light at a fixing circuit polarized light. You can get the different intensity contrast. In this way, you can measure the magnetization contrast here. It's very easy. However, only measuring the magnetic contrast is not interesting enough. The part important is that you can also measure a certain element, the magnetization from a certain element, because we have many elements in our material. So this is a so-called the absorption absorption age you can find. Because a different material, you have a different absorption age. Absorption age means you need to go to a minimum energy to get absorbed, right? To the single radiation absorbed by the electron to go down. Because a different element has a different binding energy, different co-level energy. So you will go to, for example, from this one and this one. So you can choose, this is indicate a different material, so you can choose a different energy here and to get the information of the element you like. You like to focus here. So the combine these both interesting property, you may have an element specific, and you can also get a domain image because you know the domain contrast by this way. So we call this XMGD, so the X-ray microcircular dichroism, as can be done in the singleton radiation here. And the system we studied is very simple. So we make a wedge. Of course, you can also, instead of wedge, to use a thin film. Then you need, if you like to do the signal dependence, then you need to come here every day, right? And if you are lucky, so basically one wedge can give you the whole information. So that way we prepare the wedge here. So in this wedge, you find if you don't use anti-ferromagnetic, you use only the ferromagnetic, pure ferromagnetic. So you have the so-called, at the low coverage, you have perpendicular anisotropy. And with increasing thickness, here's the increasing thickness. So you will go down, go to the implant. So at the beginning, you have the perpendicular. However, this only can be supported around the 3.5 monorail. And if you go to the higher coverage, so basically the orientation will go to the implant because of dipole-dipole interaction, shape anisotropy. They prefer implant. So it's difficult to get the perpendicular anisotropy here. So then, however, we put the magnets here, again also the wedge, and we put a 1 molar, 6 molar iron. So 6 molar is located at this range. Without this magnets, the 6 molar iron should behave as implant magnetically. So, and then you just check the precise structure is the same, and so on. And you can find, if you go to the 14 molar layer and the 21 molar layer here, and then you can see the typical exchange bias coupling. This is nothing new, so everything is the same. However, if you go to the 6 molar layer here, so we call here 6 molar layer, and we deposit the wedge here, the magnet wedge here, and when we take the top view here, and we use the NTD, so to take the domain image or the domain contrast here, and from this one here. So LCP just simply show you that we use the left circuit polarized line. Okay, and you can see, so basically here you can see the white part and it's different from the black part here. Here's the speed contrast here, and here's the gray part. And later we will see here is actually the implant direction in this direction. And this one, after 2 molar layer, here, all of this part here, actually is the implant region. And you can see here, after 3 molar layer, you can hear the perpendicular part. And how do you know that this is a perpendicular part? We like to solve the 3-dimensional magnetization. Then you need to, then the one measurement is not enough. You need to perform the 2 extra measurements. So we go to the further measurement here. This instant perpendicular anisotropy only sensitive to the perpendicular anisotropy along this direction. Okay? And then we change basically the the singleton radiation instant direction from this direction to this direction here. And you can see that we should change the contrast in this part, and here should be remain almost the same. Okay, so you can see here we already changed the reverse this part here. Of course, we cannot switch the singleton radiation. We switch the sample, okay, the code here, and then you can see if we change from the left circular pole line to the right circular pole line. So basically, you should change all the contrast. So you can change not only the implant direction here, and you can see here is the perpendicular contrast remain the same. But after changing the circular polarization, you change everything here. So in this way, you determine the all of the three-dimension magnetization distribution in this very simple sample. I think this experiment take actually one need 1 day, but one needed to many times to prepare such the detailed sample. So then we know that the conclusion is we found after 2 monolayers a new kind of spin reorientation transition. Because with increasing magnetism, you can even switch the implant direction to the perpendicular anisotropy. You provide extra perpendicular anisotropy with material of the 0 nanomoment here. So, okay, and here's just compare. You have to check if we have problem with the wedge. So we compare to the plane, only the one plane. So you can see that you need to work on every day, on several days, different days. Okay, you can find here the implant, 6 monolayer, and N means the N monolayer of the magnesium here is the implant. And slowly go up. So starting from 3 monolayer, you can find a very strong perpendicular anisotropy. Here's measurement of the perpendicular anisotropy here. And here is, you can see here is a very strong perpendicular magnetization. So this is another independent evidence of the existence of the perpendicular magnetization. So we can see also the perpendicular anisotropy, the perpendicular hysteresis group here has also very strong coercivity. And as I mentioned to you, the coercivity enhancement is also one of the fingerprint of the exchange coupling between the anti-ferromagnetic and the ferromagnetic material. So the fingerprint for the exchange coupling between iron and magnesium. But this is an indirect evidence to prove that the exchange coupling between both. So we need to do more and try to measure directly the interface orbital moment, which usually is responsible for the perpendicular anisotropy. So I would say skip to this one, and you can see here, along with this measurement, you can shift the range of the perpendicular anisotropy from the 3 monolayer to the 10 monolayer. So that you significantly enhance the working range of a perpendicular anisotropy by simply using one anti-ferromagnetic layer. So this is the first point here. So I will show you also that I mentioned to you, so we can also measure the magnetization of the different elements. In the first image, I just show you the image of the iron film, ferromagnetic film. And here I will show you, here is iron and here is magnesium here. By using different photon energy, I can choose the different absorption age. As you can see here, so this part here is from the iron, and this part here is corresponding domain. The domain shape is the same, and you can get also the magnesium at the interface. You may have also the anti-parallel net moment from the magnesium here, and this is not due to the iron contribution, but due to this actually due to the magnesium here. So magnesium provides a very, very tiny magnetization also at the interface here. So then the perpendicular anisotropy you can see here, if you combine, you choose a suitable parameter, you can get simultaneously both. One is the exchange biosphere, and another one is autoplane. So you can combine the both function, which usually be used in different material, different system. You can put the two functions together by simply put one anti-ferromagnetic layer in this system here. So this is the very good unit here. So I will not go into the detail here. I will just show you the physical region. And you will ask, that this permittivity anisotropy could be simply due to the interface anisotropy because you change the interface. However, as you see, so if I enhance the thickness of the magnets, so basically you enhance also exchange coupling. You enhance also the perpendicular anisotropy. So if this is only the purely interface property, basically the effect of this property, the effect should be independent of the thickness here. So then we will ask in the following, how antiferromagnetism drives the magnetization. So we need to find why. So the same, we use the same techniques. However, in the image, we simply use the qualitative image. We didn't go into the detailed analysis of the value of the magnetic anisotropy. And so I will show you. So with the so-called the XMCT sum rule, so basically it can provide you quantitative estimation of the magnetic moment. The magnetic moment basically is you have two parts of magnetic moment. One is the orbital part, and this one is the spin part. So usually the value of the magnetization determined by the spin moment, and the orbital moment is usually I think it's much smaller than spin moment. However, it's very important for the magnetic anisotropy because orbital moment has a very strong spatial anisotropy. So this part, if you go into very high value, so that means this system has very strong anisotropy, so which prefer a certain direction here. So to measure this part here, so can give you a physical region of this magnetization system. So then, however, this part is too complicated because you need to estimate the different physical quantity which cannot be obtained from the experiment. So then you can rewrite against and to get the simple part here. So simply go to the ratio here. So and you perform the measurement and to get the integral of the area here. So you get some value from the experiment, and which is corresponding to the ratio of the magnetic orbital moment to the spin moment here. So then we measure this part, the ratio. Then because the spin moment here is almost constant in this system, so we can say if we get an enhancement of the orbital moment, then we know, okay, this should have very strong orbital moment. And if you have very strong orbital moment, then you should have a very strong magnetic anisotropy. Okay, so just try to measure and so on, measure, and to get some information of this part here. And the HC is a hysteresis rule. If you have very strong anisotropy, then it's very difficult to switch the magnetization from this direction to another direction. So here we call it the coercivity field will become very strong. So the coercivity here is also a kind of fingerprint, of this system here. So we going to both together. So we measure. So I emphasize again, we can measure the orbital moment from the ion film and from the magnetic field. And actually, this is very difficult to measure this part here because the signal is very small. So we can see here, so with increasing temperature, so the ion film here remain the same. The orbital moment remain the same. So that means the anisotropy should be almost the same. And you can see here, we go here, the HC is indicated the perpendicular anisotropy, the strength, in a macroscopic point of view. So it's corresponding to this data point, the square is the data point here of the orbital moment of the magnetism here. So this one, if it goes small, so basically the whole system, the anisotropy of the whole system also goes small. However, the magnetic anisotropy term here, the orbital moment here remain the same. So this can also see you the very important result. So the perpendicular anisotropy of the ion layer is basically induced by the magnetism on pin orbital moment instead of the orbital moment of the ion field in the normal system. So the other system actually is the permittive anisotropy is determined by the the orbital moment of the ferromagnetic layer. However, here actually is the perpendicular anisotropy of the whole system is due to the anti-ferromagnetic system here. So that come to the very quick conclusion. So the perpendicular anisotropy causes the FM and FM exchange coupling. So actually it's due to the unpinned orbital moment and so on. So, and this is actually indicated a new future of anti-ferromagnetism. So the anti-magnetic material can not only provide the enhancement of the coercivity field and also the exchange bias field, but also so you can provide you a particular anisotropy. And this also become a new building block of the spintronic device here. So I'll come to the next part of the spin orbital part of spintronics here. So all of the spin interesting play around actually is only concerned the spin configuration in the material here. However, in the transport property, if you consider, so you have the spin up and spin down. So if you go further transport in the material, so you will forget what kind of spin you have. Because after scattering, you will give the angular momentum to the scatter. So basically, the spin cannot be kept with the same value. So then, after many times scattering, okay. So in the end, you don't know what is the spin in average. So you lose your spin memory actually in such way. So because you have a spin scattering. However, if you can design a certain material, so in a nanoscale, so you can still keep the spin memory. And this spin memory can give you a different transport property. So the most simple way is the so-called spin scattering. So you find a different transport property for spin up and spin down electron. So there are different kind of the spin-dependent transport. I think the first one is nothing to do with the spin over the coupling here. So simply just to say we have a Lorentz force if you apply the very strong magnetic field. So so basically you can change the motion of the electron and enhance the scattering path. So the scattering probability enhanced will cause your enhancement of the magnetic of the resistance. Fortunately or unfortunately, such kind of the magnetic resistance is very small, only 0.1%, even less than that. So we call this an ordinary magnetic resistance. So this magnetic resistance is very difficult to be used in our application because it's very difficult to distinguish. So you need to apply very strong magnetic field to get the resistance difference. So the one important here, so I'll show you this one. Important is so-called giant magnetic resistance here. So I'll show you this one. It's very important. Why we call this the giant? So actually it's not giant, much giant actually than the closal and the tunneling. Here actually the magnetic resistance difference is not much larger than the giant magnetic resistance here. It's simply because this is higher than this one, ordinary behavior here. And this one, so you can see the giant magnetic resistance around, of course, this is all values. Right now it's 10% or 20%, and this is already several hundred percent already here. So this is very small also, 2%, and this is much larger. But unfortunately, you need to work at a low temperature, and also the high field here. So it's not, cannot be used in the device here. So the GMR and the TMR are important in the device. And so that's the basic principle of the so-called giant magnetic resistance is due to the spin-dependent scattering. If you consider, if we have the tri-layer, the very simple layer, and this here is several nanometer only. So you have a spin up here, go to, and assume you have a higher probability go through this material if you have the same direction of the spin here. So you have parallel spin. If you have a spin down here, for example, you will scatter back, you have a higher probability to scatter back. So basically you have a higher resistance. So if you have the anti-parallel configuration, so it's anti-ferromagnetism and ferromagnetism. So then you will scatter back here at this position. For this spin, you will scatter back at this position. So then you have the higher resistance. So by changing the relative orientation of both there, so basically you can control the resistance here. So that we will call this a magnetoresistance. And this is also the basic principle of the Spintronics application. So you control the magnetization here, so you can control in turn the resistance. So this is the basic idea. And this idea has been realized in 1998, and they got the Nobel Prize in physics of 2007. Actually, one of the major reasons is because of the application. You go to see the application, the impact of this fundamental finding in the application, you can find. This is a 1990, so here. So 1990 here. So here's still the old type of the magnetoresistance head here. And 1998, they found actually the GMR material, and you can see the GMR has been applied in a hard disk as a read head. Because if you change the magnetization, you can simply measure the resistance. So this function can be used as a read head. So very sensitive to the read head. So if you can enhance the sensitivity of the read head, so basically you can enhance significantly the storage density. So here you can see in 1997 here go up is you have the slope here, the king go to slope. So that here is the low density is go up here, and this simply killed the company using the old magnetoresistance techniques here. This is I would say this is a standard example to see this is a kind of the killer technology can really kill a big company. And this company, which use the old magnetic technology, actually have the market sharing around 50% and 60%. And even though if you can find a new technology here, so that they will disappear. That company disappear here. So let's show you this is the impact of that. And from the fundamental research to the very high application is only less than 10 years. And this example also tell you, so basically it's very difficult to distinguish what is so-called fundamental research and application research, because you can buy the technology which has been found 9 years ago. You can already found it in the Guanghua market, Guanghua Sangcang. So only less than 9 years. This is an example of here, changing you a lot here. So, and another way to get a spin-dependent tunneling, a spin-dependent transport is so-called the spin-dependent tunneling instead of the scattering. Okay, so this is can be understood by the density of state, spin up, spin down. So that in 1975, the jury already proposed a model to describe the spin-dependent tunneling, proposed actually experiment. But only 20 years later, so 1995, so one can only design or fabricate a sample at room temperature to present the spin-dependent tunneling here. So you can see, because spin-dependent tunneling itself is a spin-free transport, so the spin down can only go to the spin up, and spin down, and spin up can only go to the spin up here. So we can go to here's a more occupied state, go to the more occupied state. So you have a higher probability to go from this side to this side, and here's a less probability to go to this side. But at least you have a channel, at least a higher probability of the connectivity, higher probability of the transport. However, if you change the direction to the anti-parallel, so basically you can get the less conductivity, then you have the lower conductivity. So this is similarly, you can also build up your magnetoresistance, but due to the different so-called reason. So basically, the interface correlation of the magnetization configuration will determine the resistance of such field. Because this is should be tunneling, then this should be insulator. So about the 2 nanometer aluminum oxide or the MgO will be used usually in such material. So basically 2 nanometer. Then it's enhance the difficulty